Okay, so where we left off, we were talking about the layer 2 devices for Ethernet. And one of the big functions of the layer 2 Ethernet switches is that they're going to define who can talk to each other based on the broadcast domain. Or from our configuration point of view, this is what we're going to be defining as the VLAN. Now, some of the design issues that we could run into layer 2 Ethernet designs is one of the first ones is that there's a scalability limitation based on how many devices are in the collision domain. Where in today's networks with wired Ethernet switches, this is not really a problem because we're defining the collision domain on an individual port basis. Where we would see this as still a problem in today's networks is with wireless or with Wi-Fi, because all of the devices that are in the same wireless cell are going to be competing with each other for the bandwidth. They're going to be in the same collision domain. With Ethernet, originally this was the half duplex problem, where you're using the same physical cables to send traffic and receive traffic. So you had to listen to see if someone else was sending before you sent a packet onto the wire from a layer 1 point of view, which is what the CSMA-CD means, the Carrier Sense Multiple Access with Collision Detection. We also have a problem that is related to this with the physical network size and the amount of delay that it takes a frame to get from one side of the cable to the other side of the cable, because the end devices have to listen for what's known as the collision detection window, where essentially how long is it going to take me if I send the frame on one side of the wire, how long is the actual electrical delay to get to the other side, and that's ultimately going to control how long you have to wait before you can hear someone else sending. And then if you don't hear someone else sending, you can send your own frame and then assume that it's not going to run into someone else's. So for half-duplex Ethernet, the way that they fix the problem with this is that this Carrier Sense Multiple Access with Collision Detection algorithm that uses what's known as a jam signal, that if my electrical signal runs into someone else's, they're essentially going to cancel each other out. And the hosts tell the rest of the network that happened by sending a jam. With layer 2 switches, this is what we're mainly solving, that each of the ports are in their own collision domain, which means that they can run in full duplex. I can send traffic and I can receive traffic at the same time, because from a physical point of view at layer 1, I'm using a different cable to send my traffic than I am to receive my traffic. As I mentioned, in the case of copper cables like Cat5 or Cat6, you use a separate pair for sending than you do for receiving. Or in the case of fiber optics, you have a separate send channel than you do the receive channel. We would also see that even though we're solving this problem with the half-duplex communication or the collisions, there's still a limitation in layer 2 networks based on how many total hosts you have in the network. And the reason this is a problem is that when the layer 2 switches are trying to figure out where are the sources located and where are the destinations located, it's trying to figure out what are the MAC addresses of the machines. So when I receive a frame, I actually know where to deliver it in the network. Again, this is what the MAC address table or the CAM table is used to do. So when a switch receives a frame, it's going to look at the destination value. It's going to correlate this against its own MAC address table and try to figure out which physical port is that device actually located on. But the problem we run into, or one of the problems we run into, is that unlike IP routing, there's no hierarchy to the addressing format that MAC addresses use. So if you have one vendor, let's say you have an Intel NIC card, and then you have some other vendor for a different NIC card like Broadcom or something like that, they're going to have different addresses based on the vendor codes that were assigned to them. So there's no real clean-cut way in order to do summarization of the MAC address table, unlike we can in IP routing. So when we get to the specifics of like eHRP, OSPF, BGP, one of the big design things that we need to take into account is how are the addresses assigned to the devices, and can we summarize them or combine them together into larger supernets so it makes the routing table size smaller. But in the case of layer 2 switching, we cannot do this. So this means that if you had a network that was made up of 50,000 hosts, it means that each switch would have to hold 50,000 MAC addresses, and even down to your access layer. And a lot of times you'll see that this is one of the limitations of the different platforms, is how many MAC addresses do they actually have space to hold. So although in the core of your network maybe you have like a 6509 that has tons of memory, When you get down to the access layer, if you have like a 2950 switch or something older than that, it's going to be able to hold many fewer MAC addresses. So we'll see that when we talk about layer 3 routing, this is one of the optimizations that we're doing by separating the network not only into different broadcast domains with VLANs, by separating them into different layer 3 networks. We don't have to have visibility of the MAC addresses everywhere in the topology. Now, one of the additional problems that we run into with this is that if the switch does run out of memory, it basically turns back into a hub where all of the ports basically flood traffic everywhere regardless of what the destination is. So once it's out of memory or once the MAC address table is full, it's going to treat all frames like they're broadcasts. And this generally could happen for two reasons. One is just that your network is too big, or the other one, someone is running an attack to try to flood the MAC address table. And one of the common ones to do this is an application that is known as MAC OFF or MAC OF, where we'll talk about this in more details when we get to layer 2 security. But this application says flood the switch LAN with random MAC addresses. And basically what this is designed to do is eat up all the memory on the switches so that when someone else sends a frame, I'm going to receive it, regardless of whether I'm in the same VLAN or not, or regardless of whether I'm in the same broadcast domain. The logic of the switch being able to keep track of where the hosts are, it kind of breaks down when it runs into this problem or when it runs out of memory. The way that we're going to solve this, as I mentioned, is by using layer 3 routing. So whether the switch is the one doing this or whether we have a dedicated router, as we're moving our layer 3 packets between interfaces, the router is going to be changing the layer 2 header or doing what we call the layer 2 packet rewrite. So this means that the MAC addresses on one side of the link are going to be locally significant to that interface, and we don't necessarily care if they're on the other side of the link. So instead of making our forwarding decision based on a layer 2 MAC address, we're going to be making it on the layer 3 IP address as opposed to the MAC. Now, another potential issue we run into with these layer 2 switching devices is the size of the broadcast domain. Because as I mentioned, everyone in the same LAN segment or the same VLAN is able to address or able to send packets to each other by using this all hosts address, which is the all ones value of the MAC address, or essentially the all Fs. One of the potential issues you can run into with this is what is known as a broadcast storm, which basically means that too much of your bandwidth is taken up by these layer 2 frames, these layer 2 broadcasts, to the point that the network could potentially be unusable. So we'll see that when we get to layer 2 spanning tree, this could be a potential issue we need to deal with, and then ultimately by using layer 3 routing, this is going to be one thing that we can use to fix this. Most of the time, just like the MAC address table filling out, it means that either your network is too big, or it could be that someone is trying to poison the layer 2 CAM table or to try to generate these flooding attacks. In the case of a legitimate problem, this could be like an address resolution protocol storm or a broadcast storm where someone is sending the frame to that all Fs address, and they're trying to do it for a legitimate reason, but if the network is too overloaded and they don't get responses to that, basically it's going to knock everyone on the VLAN off of the segment. There are some illegitimate reasons as well. One of them is known as the Fraggle attack. There's also another variation of this that's called the Smurf attack that's basically designed to flood the LAN segment so that all the bandwidth is used and that the segment is unusable. And again, we'll see in security some of the different ways that we can prevent these type of attacks. But in general, the main fix of this is that we're going to limit how many hosts per segment. Typically, your VLAN is also going to map to your IP subnet, and the VLAN may have like a /24 subnet assignment to it, which means it's going to have about 250 some hosts on the network. Now the next device, as we continue to move up the OSI stack or the OSI model, is going to be our layer 3 routers, where the layer 2 switches are going to be forwarding their frames based on the destination MAC addresses. The layer 3 routers are going to be forwarding packets what we call our layer 3 protocol data unit, or layer 3 PDU, we're going to be forwarding the packets based on the destination layer 3 address. Whether this is an IPv4 address or an IPv6 address, the logic is the same. That we're going to be using a layer 3 routing table as opposed to the layer 2 MAC address table in order for the routers to make their decisions. Now, the key additional feature that the router has to do here is for every interface that we move a routed packet between, we need to rebuild the header. And this is one of the reasons that layer 3 routers are generally slower than the layer 2 switches, because the layer 2 switches don't need to change anything in the frame. They're just moving the frame between interfaces. But a router always has to do what we call the decapsulation, or basically removing a portion of the data. In this case, it's the layer 2 header, and then rebuilding it or re-encapsulating it as it's going out the destination segment. And one of the main advantages of doing this is that the router then can be used to connect two different segments of the network that use different layer 2 encapsulations. So on our side of the network, maybe we have Ethernet that's used for our LAN, but then as we go to the wide area network, maybe we have a PPP interface that's running over like a T1 or a T3 or higher. The router is going to need to change the protocol format as it's moving between the interfaces. Now generally we'll see that the router doesn't change the frame other than this layer 2 value. There are going to be some corner case scenarios that it does do a modification, like in the case of network address translation, where we might be changing the source address of where the packet came from, or in the reverse direction we might be changing the destination of where it's going. But in the vast majority of cases, the router leaves the IP packet alone, and it's just going to be changing the layer 2 header as it moves between the interfaces. This also implies that all of the router's segments, or all the router's ports or links, are always in separate collision domains, and they're always in separate broadcast domains, where the router is not going to send a layer 3 or a layer 2 broadcast between its interfaces. The other disadvantage of this when we're talking about a traditional layer 3 router is most of the time they're doing their forwarding in software, unless we're looking at a really high-end or specialized router like ASR, CRS, 7600, that type of stuff, where those would be hardware assist forwarding. But most of the time, routers in general are going to be slower because they're making this decision in software. So then we have the layer 3 switches as well, which just like the routers are going to make a decision based on the layer 3 packet, like the IPv4 or the IPv6 packet. But the difference is that the rewrite of the frame is going to be hardware accelerated, where technically like a 7600 router is a layer 3 switch, basically the same as like a Catalyst 6500. This actual rewrite process is sometimes also called the switching path. Now we'll talk about this when we get into more details of the actual router's operation. But the slowest of these rewrite processes, or the switching path, is what's known as process switching. Process switching basically means that for every packet I move between interfaces, I have to ask the general purpose CPU, where is it going and how do I rebuild the frame? So this is going to be an interrupt-based CPU forwarding. This is going to be the slowest of them. Cisco also has some additional forwarding paths like fast switching, which means that you route once and you switch the rest of the packets. So you're building what's known as this flow cache, or the fast switching cache, that you ask the CPU, what is the layer 2 frame supposed to look like? Then for all other packets in the flow, you can use this value that was cached. Another variation would be net flow switching, which used to be called multi-layer switching, or MLS. Basically, it does the same type of thing as fast switching, just uses a little bit faster caching algorithm. The one that we use most of the time nowadays is called Cisco Express Forwarding, or CEF, where the idea behind this is that we have a separate routing table versus a forwarding table, where the forwarding table pre-calculates what is the layer 2 header going to look like when I'm going to these different destinations. So the router is automatically going to know what is the MAC address of the next hop on the link. Or in the case of frame relay, what is the DELC number? Or in the case of ATM, what is the VPI, VCI? So then we can ask this forwarding adjacency table, or simply the forwarding table, in order to figure out how to build the frame as we move it between the interfaces. This is the one that the very fast hardware accelerated platforms use. Like in the case of like a CRS or a GSR, the actual port, or what we consider the line card, so the physical interface like your gigabit Ethernet link or your OC48 optical interface, the interface itself has a copy of the forwarding cache or the forwarding table. So you can run into cases where the frame comes in one port, goes out another port, and it doesn't have to ask the CPU, how am I supposed to forward the traffic? Now we'll see the reason that this is important. What are the differences in the switching paths? Is it has to do with those features that we start to add on the routers. There are certain cases like doing accessless and accessless logging that you would force your traffic to move from the Ceph switching path down to process switching, which means that your CPU could have a very high utilization if you don't have the feature properly configured. And one of the ways that you would see this problem in a real network design, if you were to look at the show processes CPU or show proc CPU, the router is going to give you two different counters here where it shows your CPU utilization. One of them is the interrupt utilization. One is the regular utilization, where if you see this first value is really high, usually this means that there's a problem in your switching path, where something that is supposed to be Ceph switched ends up being process switched. And basically all of the platforms except the really, really high-end ones like CRS or GSR, you wouldn't have these problems. But even like the 6500 or the Catalyst 7600, the general purpose CPU is pretty slow. So if you start having to use this process switching path, it can be real easy for the utilization to get out of control. So we'll look at some more details of this when we get to the different router features. But this is one way that you can see that this is the problem. If you say show proc CPU or show proc CPU history, this is going to give you a graph of the utilization. And then you would know, is the router having problems in forwarding because its CPU percentage is too high? Mohammed?
You said the forwarding tables are actually, a copy of that table is stored in the interface?
Is stored in the interface itself, right.
It's in the DRS or all platforms?
It depends on the individual platform.
Okay.
So in the case of, and let me see if I can get to it from right now,
Let's say if it is just an IRS standard.
If it's just a regular enterprise platform like a 1800, 2800, those are all software forwarding.
Okay, so
In the case here, this is a GSR that's running iOS XR. If we look at here, the show inventory, which shows the hardware table, and not show inventory. I need to say show diag. Okay, this one here has the general purpose CPU is the performance route processor, or PRP, what they call it for the GSR platform. So this itself has 2 gigs of RAM for the router's CPU. But then when you look at the individual line cards, the forwarding card, which in this case here, this is an OC48 packet over SONET interface, this actually has to have memory for the routing table itself, because the general purpose CPU calculates the routes based on like OSPF or EHRP or BGP. Then it sends a copy of the Ceph table or the forwarding table to the line card. Okay. Then the line card can work independently of the general purpose CPU. So the really fast platforms, this is the reason they're able to get line rate, is that the forwarding table happens at hardware at the individual port, where the enterprise platforms, like that you would hook up to like your cable modem or maybe T1 or T3, those are going to have a lot less forwarding capability when you compare it to the interface. Like you may have fast Ethernet, but I might maybe only be able to get 15 megabits per second on fast Ethernet, because you're constantly having to pull the software process to figure out where the packet is going to go.
And in the switches, is ASIC being used for those tables? Or?
The ASIC is being used for the layer 2 switching. Okay. It may not be used for the layer 3 switching, which is generally why your routing process is going to be slower than your layer 2 switching process. And again, one of the key reasons why that's a problem is that for layer 2 switching, there's no rewriting of the packet. So when an Ethernet switch receives the frame in one port and forwards it out another one, it's not changing anything. But in the case of the router, you have to look at the destination, strip the old header off, build a new one, put that on, and then forward it. And this is happening on a packet-by-packet basis.
Is that a general rule of thumb that the ASICs are used for layer 2 and not layer 3?
Depends on the platform, but in general it does. So in today's networks, when we look at like a layer 3 switch or multi-layer switching, usually the key is that this is a hardware-based implementation of the Cisco Express forwarding process. So you would see like the switches that we use here. In this case, if we were to look at the show version, this is a 3560. In this platform, you cannot turn Ceph off because it's implemented in hardware. This is one of the reasons that the switches have much less functionality with layer 3 features versus the routers. So you may be able to do some basic forwarding like doing OSPF routing or EIGRP routing, but one of the things the access layer doesn't support is like network address translation, because you have to do a further rewrite into the packet, and that's going to take more resources in software than it does in hardware. Or things when we look at the quality of service features of the layer 2 switches versus the routers. QoS implementation on a switch is pretty simple as compared to the router, because there's not as many things that you can change or not as many things you can look at inside of the packet. Now as we continue to move up from there, some of these switches could be considered both layer 3 and layer 4, where the layer 3 device is going to make its decision based on the destination IP address or the destination IPv6 address. So where a layer 2 switch makes this decision based on the MAC address, the router is doing this based on the IP packet. The problem with this is that in some network designs, you end up in a case where you have multiple paths in the network, or maybe multiple equal cost paths, but some of them end up being more utilized than others. Because if you were doing, let's say we have one centralized web server in the network or some centralized database server. When the router makes its decision, if it's always forwarding the traffic to that same destination, it's always going to pick the same interface to forward the traffic through. So in addition to the normal layer 3 lookup, and this problem here, sometimes this is called Ceph polarization, where when I make my forwarding calculation, it always points at the same interface, even though I have multiple options. The way that we can fix this is by having the Ceph process use the source and destination ports of the layer 4 packet as well, which is going to be based on either TCP or UDP. Like if we're using web browsing, when you go to the server and you make a request at port 80, and if we were to try to visualize this here, if we have this client on the left trying to hit a web server that's on the right, when we go through our TCP negotiation at layer 4, the end host is going to say, I want to start the TCP session. And the way it does this is by sending a TCP synchronization packet, or a SYN. This is the first portion of the TCP three-way handshake, where the server is then going to reply with what? It's going to reply with an acknowledgement saying, I know you want to start a session, and I also want to start the session. So it's an ACK SYN or a SYN-ACK. Then the third portion is the originating client is going to send the acknowledgement saying, I now know that you want to start the session as well. Now we can actually send the data. But during this exchange, the source port and the destination port are going to be negotiated between the applications. Where the destination port in case of web browsing is going to be what?
80.
Is going to be 80. But the source port is going to be something that is random. The actual value that's chosen depends on the different sessions that the web server has open. So if I'm already receiving web requests from hosts that are using the same IP address, I'm going to tell them to use different source ports so I can tell one session apart from another one. And the key with that is that since these values essentially end up to be random, you can use this as part of your forwarding decision to try to get a more diverse path selection if you have multiple possible interfaces that you can use. And in the case of layer 4 classification, this is known as the network flow, where the flow is the combination of the source IP address, the destination IP address, the source protocol like TCP or UDP, the source port, and the destination port. The key with this is that you can still hardware accelerate the implementation of this. And again, this is going to depend on the platform, but it allows it to make a more granular decision as to how the traffic is forwarded. And you can actually see this on some of the routing platforms. If you look at the show IP Ceph exact route, the exact route will tell you or ask you what is the source address of the packet and what is the destination address of the packet, where normally it's assumed that the routing table makes its decision based on the destination. In the case of Ceph, this platform actually does it on both. So we'll look at this when we get into more details of routing, that if you do have multiple equal cost paths and you're trying to forward over both of them, this is one of the advantages of using the Cisco Express forwarding, is that based on the input of the source and the destination, the router can choose which interface am I actually going to forward the traffic over.
To load balance?
To load balance the traffic, right. If there's only one link between me and you, then it doesn't matter. It's whatever the routes that I'm learning out that interface, that's where it's going to forward. But this would be needed if you were to have some design where maybe I have my end host A that connects to my switch. Then at the distribution layer, these are my routers. And let's say these are like WAN links. If I were to have two T1 interfaces, when the routing protocols look at this, and from a real simplistic point of view, assuming that everything else is equal up to this point, router 1 would say I could use serial interface 1 to reach the destination, or I could use serial 2. If both of those entries are installed in the routing table, it still needs to choose which one am I going to actually use. And this is what the layer 3 and the layer 4 switching does for us, is that the router can do the classification based on not only the IP source and the IP destination, but also based on the port pairs at layer 4. So as I mentioned, some further readings on these topics. It's kind of more high level, where we're just talking about what are the different roles of devices in the network and then how are they going to fit into the design. But a lot of this detail is going to be covered under the Cisco Validated Design Program, or what used to be called the Solutions Reference Network Design Guides. So this one here, the Enterprise Campus Architecture Overview, this is the one that I was showing before, that it'll have what are the different devices, like what happens at your access layer, what happens at distribution, what happens at the core, then how do the different pieces fit together? Like HSRP for high availability, QoS markings for dealing with your IP voice traffic or your IP video traffic, and then also this one, the high availability campus network design. Okay, any questions up to this point on just the general overview of the 3-layer model, or where the different devices are going to fit that we're talking about?